Hi, so welcome to the review for chapter 11.2. And I want to discuss the stability of points for linear, starting with systems that are linear and autonomous. And let's start with this problem 1. In problem 1 through 8, this is problem 1. The general solution of the linear system x prime equals ax is given. So they're telling us, hey, you have a system of this form, and I'm giving you a solution. That's your solution. So what we used to do is find the solution ourselves, but here they want us to focus on just looking at the solution. In each case, discuss the nature of the solution in a neighborhood of 0, 0. Well, what happens at 0, 0 if I just focus on my solution? The nature of the solution in the neighborhood of 0, 0. And for these questions, really what I want to ask is the behavior around some sort of critical point. And the behavior around a critical point can sometimes be analyzed by simply answering the question, what is the limit as t goes to infinity of my solution? And this is where we start. Then obviously, sometimes we cannot find the solution. We cannot solve a nonlinear system. And so we resort to other techniques to classify the critical points. But in this case, since they give us the solution, all we have to do is say, okay, well, if this first solution, well, I'm not going to write it because it's going to be something else. If this gets larger and larger, this becomes a smaller and smaller number, because if I have like 2 to the negative 1, that's going to be 1 over 2. If I have 2 to the negative 2, that's going to be 1 over 2 squared, which is going to be 1/4. If I have 2 to the negative 3, that's going to be 1 over 2 to the third, which is equal to 1 over 8. So you see how these numbers are getting smaller and smaller, and they eventually get to 0 if this is large enough. So if I have like 2 to the 10, that's going to be 2 to the 5th times 2 to the 5th, to the negative 10, sorry. That's going to be 1 over 2 to the 5th times 2 to the 5th, which is 32 times 32, which is going to be a small number, and it gets smaller and smaller as this increases. And if I want to look at the limit as t goes to infinity, and there's a negative in front of that infinity, because there's a negative in front of that t, then we're approaching 0 for this number. And for this number, we're also approaching 0. So eventually, we're approaching the point 0, 0. And another thing that might be confusing here is that they are pretty fluid between this notation, which is horizontal, 0, 0, and the vertical notation here. So just keep in mind that when they mean 0, 0, this is my x, and this is my y, which corresponds to what value we approach here and here, and not this specific vector, but the sum of these two vectors, because you can rewrite this solution as 2 vectors by distributing this guy in here, and this guy as well, and by distributing this guy in, and then adding them together, you'd have just one 2 by 1 vector, and that's what they mean for the approaching some sort of point. So this will approach the vector 0, 0, which is the same as the point 0, 0. And so that's the answer to our first question. What is the nature? What is the nature? Because of this, the nature is a stable critical point. Now, let's look at B. With the aid of a graphing utility, plot the solution that satisfy x of 0 equals 1 1. Okay, so with the aid of a graphing utility, we want to plot this. Well, the first thing that we need to know is the values for C1 and C2, because those are going to incorporate this initial condition, which is going to allow us to actually tell the graphing utility to compute that. So let's go and write x of t, nope, because they tell x of 0 is equal to 1, 1. We switch from horizontal to vertical matrix, is equal to C1 times 2 minus 1. E to the 0, we're substituting 0 for t, plus C2. That's why they're called initial conditions, because they start when the time is 0 in the model. Because yes, we can use all of these to model some real phenomenon. And so this is 1, 2, and then we have e to the negative 6 times 0. So that means anything to the 0 power is just going to be 1. So this is going to be 1, and this is going to be 1. Now, as I was saying, we can distribute the C1 and C2. So we get 1, 1 here, and this vector equals to 2 C sub 1 minus C sub 1 plus, at the top, we have C sub 2 and plus 2 C sub 2. I just distributed, and then I combined two steps because I also added the two vectors together, entry by entry. And so now we can split this into two equations. We can see we have the top equation, 1 is equal to 2C1 plus C2. And then we have 1 is equal to negative C1 plus 2C2. Now, if I multiply this bottom by 2, because I know that if I multiply by the same side, both the left and the right, nothing will change now. But the thing is that if I multiply this by 2, what happens is that this becomes a negative 2c, and this becomes, oh, this was already a 2, so this becomes a 4c2. And now I can add them together. Now, why can I add them together? Well, because this equation is telling me that this left-hand side is equal to this right-hand side. So adding this bottom equation to this top equation is the same thing as saying I'm going to add something to the left and something to the right, and it's not going to change the equality. So now, what are we going to do? Well, we're going to have 2 here. 2 times 1 is 2. 2 plus 1 is equal to 3, and that's equal. And why I did this is because this cancels out. So now we can only deal with the C2. We have C2 plus 4C2, which is 5C2. So C2 happens to be 3/5 if we divide both sides by 5. And now that we have C2, we can plug that back into any of the two equations. So I'm going to go with the top one. 1 is equal to 2C1 plus 3/5. And so we get 1 minus 3/5 equals to 2C1. So now we're going to have 5 minus 3, which is 2/5, divided by 2 is going to be equal to C1. So eventually we have that C1 is equal to 1/5. And so these are our two constants that we need to put in front into the graphing utility. So what are we gonna tell the graphing utility? The graphing utility, I'm gonna use calc plot, and you're gonna see is gonna tell me what is my P of X, Y, or in this case P of T, sorry, and what is my Q of T. And I think there was another letter, I don't remember, PQR, I guess it's R, and this one's going to be 0 because we have no third equation, and this makes it a plane autonomous system. It's literally because we can represent it in a 2D surface. So, in a 2D plane. So, my PT is going to be the top equation with the initial conditions. So, C1 times 2 times e to the negative t. C1 is 1/5, so this is going to be 1/5 times 2, so that's going to be 2/5 e to the negative t. That takes care of the first term. Second term is going to be C2 times 1 times e to the negative 6. C2 we said is 3/5, so plus 3/5 times 1 times e to the negative 6t. And then we have this other equation at the bottom, which is going to be what? It's going to be let's go over here, and we're going to have C1 times -1 e to the negative t. So -1/5 e to the negative t. And then we have C2 times 2 e to the negative 6t. C2 is 3/5. So we're going to have 3/5 times 2, that's 6/5 e to the negative 6t. Okay, and now that we have this, what we want to do, is we want to put it in a graphing utility. And I'll see you there for part B.